Hello, welcome to week 9. We're now in the second half of the course. Can you believe it? This week we're talking about divisibility and prime versus composite and factor versus multiple. Our objectives for this week: we will be discovering and applying divisibility rules, distinguishing between prime and composite numbers, be able to explain and find how many divisors there are or factors for any number, find the prime factorization of a number. We'll also be starting to talk about least common multiple and greatest common factor. So divisibility, what does the word divisible mean? Is 72 divisible by 2, 3, 4? Think about it. How do you know? The word divisible means a number is divisible by another number if that number divides the number evenly with no remainder. So, is 72 divisible by 2? Yeah, it's equal to 36. 72 divided by 3 is 24. 72 divided by 4 is 18. I know this by dividing 72 by each one of the numbers to see if there is a remainder. But there are shortcuts to knowing if a number is divisible by certain factors. So you have a worksheet that goes along with this. It's called Divisibility Rules Practice. So print out that worksheet or get it ready electronically, and you can complete it while you're using the slides, or at least start, and then complete the assignment on Canvas. So first we're going to fill in the divisibility rules at the top, and then you're going to add examples for each rule. And then at the bottom of the page, there's practice problems where you have to see if numbers are divisible by other numbers. And make sure you follow directions, because it says show all your work on a separate sheet of paper. And you're not doing just division, you're going to be proving these divisibility rules with that practice activity. So you're going to test all the numbers and explain why they do or do not work. So first, let's see what the divisibility rules are. So you probably know at least some of these. So think about them for a minute. See if you know the rule for 2, 3, 4, 5, 6, 9, or 10. Okay, so a number is divisible by 2 if the last digit is 0, 2, 4, 6, or 8. Some people also like to say that rule as if the number is even. So if it's an even number, then it's divisible by 2. The other rule you might be familiar with is 5. If the last digit is a 0 or 5, the number is divisible by 5. And you might know the rule for 10. So if the last digit is 0, the number is divisible by 10. The ones you might be less familiar with, or may not even have ever been told these rules at all, are the rules for 3, 4, 6, and 9. So the rule for 3 is if the sum of the digits is divisible by 3. So if you add up the digits and that number is divisible by 3, then the original number is divisible by 3. The rule for 9 is very similar. So if the sum of the digits is divisible by 9, then the original number is divisible by 9. The rule for 4 is if the last two digits form a number that's divisible by 4. So you don't sum those digits, you just look at the last two digits as a number and see if it's divisible by 4. And then the last rule that might be new for you is the number is divisible by 6 if the number is divisible both by 2 and 3. So if it meets the rule for 2, being even or ending in a 0, 2, 4, 6, or 8, and if it is divisible by 3, so if the sum of the digits is divisible by 3. So if it meets both those rules, then it is divisible by 6. Here's those rules written out, so make sure you fill in your worksheet. Now notice over here I said be sure to make examples here. So you make up your own examples of numbers that meet those rules. You can complete the rest of that worksheet. Just make sure you show your work on a separate sheet of paper. Prime versus composite. Prime numbers are numbers that are defined as numbers that have exactly two factors, 1 and itself. Composite numbers are numbers that have more than 2 factors. Now, it is important to note that the number 1 is neither prime nor composite since it has only one factor of 1. You can probably think of some prime numbers like 2, 3, 5, and 7. We're going to use these prime numbers to find all prime numbers less than 100. We're going to use something called Eratosthenes sieve. If you've ever made cookies, you may have used a sieve to sift flour. A sieve is a device with a bottom that's full of tiny holes. It lets fine flour particles through but retains the lumpy bits. Eratosthenes was an ancient Greek athlete, astronomer, and mathematician. His sieve doesn't sort out lumps of flour, it sorts out prime numbers. A prime number is a number that can be divided evenly by only 1 in itself. And when we say divided evenly, we mean that the result is a whole number with no remainder. You have an activity on Eratosthenes' sieve, and now would be a great time to complete that activity. It doesn't take too long, but you could pause the video, go through that activity, and complete it, and upload it to Canvas, and then come back to this recording. So once you've gone through that Eratosthenes sieve, you might wonder why it's important to understand prime and composite. So understanding prime and composite numbers helps people when they're working with fractions, which is the next unit we're headed into. When students are adding and subtracting fractions, they often have to find a common denominator, which is a multiple that 2 numbers have in common. Suppose your group had to add 2/5 plus 1/6. One look at the completed chart reveals that 30 is the smallest number that is a multiple of 5 and 2 and 3, or 6. So they would know that 30 is the common denominator of 5 and 6. Another common fraction operation is writing a fraction in lowest terms. That means finding the greatest number that will divide evenly into both the numerator, the top part of the fraction, and the denominator, the bottom part of the fraction. For example, if you asked group members to write 12 over 30 in lowest terms, they would need to find the greatest number that divides evenly into both 12 and 30. The completed chart shows that both 12 and 30 are both multiples of 6. Dividing 6 into both the numerator and denominator simplifies 12 over 30 into 2 over 5. By knowing which numbers are prime, they would know that 2/7 and 12 over 23 cannot be simplified. So, one of the things that also comes out of the sieve of Eratosthenes is which primes do we need to check to see if a number is prime or composite? There's a theorem that you can develop through the activity that you did where you determine what's the largest prime number you need to check. And that theorem, so we only went up to the prime numbers less than 10, but we actually found all the prime numbers less than 100, and the square root of 100 is 10. So a theorem develops out of that you don't need to check all prime numbers up to the number, you just need to check all the prime numbers up to the square root of the number you're trying to find. So for 557, when we determine what's the largest prime we need to check, we take the square root of 557 and we check all the primes up to that. The same is true with 463. You can pause the video here and see if you get the right answers for those. We didn't check to see if it's prime or composite. All we're checking is to figure out the largest prime we would need to check. So when we take the square root of 557, it's approximately 23 and then some decimals. So we only need to check prime numbers up to 23 to see if it's prime. So therefore, using your sieve that you just figured out, we would need to check 2, 3, 5, 7, 11, 13, 17, 19, and 23. If none of those divide it evenly, then 557 must be prime. For 463, we take the square root of 463 and we get 21 and some change. So we only need to check the prime numbers up to 19. So 2, 3, 5, 7, 11, 13, 17, and 19. Once we check all those, if none of those divided evenly, we know that 463 is prime. Make sure you make sense of that before you move on. So you could think of any number you're trying to check and see if it's prime. You don't have to check all the primes up to that number. You only have to check primes up to the square root of that number. So prime factorization, now that we know what prime numbers are, we should be able to simplify numbers into their prime factorizations. So find the prime factorization of 504 and then 303. Pause the video. You've done this before. You might not use the same technique I do, but I'm sure you can get those prime factorizations. All right, here's my answer. So the prime factorization for 504, I like to use tree diagrams or factor trees. So I simplified until I had only primes. So 2 times 2 times 2 times 3 times 3 times 7, or I could write it in exponential form, 2 cubed times 3 squared times 7. The prime factorization for 303 was much easier. 3 times 101, because I know both 3 and 101 are prime. I have an additional resource listed in our module this week that you can practice finding prime factorization using factor trees online. So if you are having trouble with this, that would be a great resource for you. So sometimes you're asked to list the number of divisors or factors, and here is a strategy to do that. So the first thing you do is find the prime factorization of the number. Then you take each factor and look at the exponent. You add 1 to each exponent, and then you multiply those numbers from step 3 for all the factors in the prime factorization. And there's the theorem written algebraically for p and q as unique prime factors. P to the n, q to the m has n plus 1 times m plus 1 positive divisors. So for example, if we do the prime factorization of 12, we get 2 to the second power times 3 to the first power. So the number of divisors is we take the 2 in the exponent on the 2 and we add 1 to it. We take the 1 in the exponent on the 3, we add 1 to it. So we get 3 times 2 is 6. And then if we wanted to list all the factors of 6, they come in pairs. So 1 and 12, 2 and 6, and 3 and 4. So there are 6 factors of 12. All right, so a Freyer model. What is a Freyer model? So a Freyer model is a graphic organizer to help people identify unfamiliar concepts and vocabulary. Students define a concept, word, term, describe its essential characteristics, provide examples of the idea, and suggest non-examples of the idea. Knowing what a concept isn't is helpful in knowing what it is. So here's your Freyer model. You're going to make 2 of them. This is an assignment on Canvas. One of them you're going to write the word factor in the middle. The other one you're going to write the word multiple in the middle. These are common vocabulary terms in elementary math, and they are used incorrectly by students and teachers a lot. So this is going to be an activity where you're going to have to really think, see if you can come up with some ideas, and then when you're finished, you should have a good idea of the differences between factor and multiple. So there's also a link here on this Freyer model. So if you wanted to see how to teach a Freyer model, you could read through that explanation. So next we're going to talk about greatest common factor and then least common multiple. So what is a common factor? Let's say we've worked out the factors of 2 numbers, like the factors of 8 and 12. So factors of 8 are numbers that divide 8 evenly, so 1, 2, 4, and 8. Factors of 12 are 1, 2, 3, 4, 6, and 12. So it's a common factor when it's a factor of 2 or more numbers. So what's the greatest common factor? It's simply the largest of the common factors. So you can see in 8 and 12, they have a common factor of 1, a common factor of 2, a common factor of 4. So the largest one of those is 4. So 4 is the greatest common factor, or sometimes we call it the GCF. Why is this useful? So knowing how to find it and use the greatest common factor is one of the most useful things when you want to simplify a fraction. Least common multiple, or the LCM. So what's a multiple? We get a multiple of a number when we multiply it by another number, such as multiplying by 1, 2, 3, 4, 5, etc., but not 0. So it's just like a multiplication table or a skip counting chart. So example, multiples of 8 are 8, 16, 24, 32, 40, and 48. And notice there's dots because that goes on and on and on. For multiples of 12, that's 12, 24, 36, 48, 60, 72. Again, that goes on and on. So what's a common multiple? So those would be the numbers that appear in both lists. So right here, 24 appears in both lists and 48 appears in both lists. So the least common multiple will be the smallest number that appears in both lists. So in this case, it's 24. The least common multiple is useful when you're trying to find common denominators in fractions. Now, sometimes that listing procedure can take a long time, so I'm going to show you a new strategy that I'm not sure you've seen before, where you can use Venn diagrams for LCM and GCF. And you're probably going, oh, not Venn diagrams again. I think you'll like this because this is when you're going to use this as a tool to help you. So we're going to use numbers 18 and 12, and the first thing we have to do is find the prime factorization of both numbers. So do that now before you move on. All right, so I wrote my prime factorization of 18 on the left side, so it comes out to 2 times 3 times 3, and my prime factorization of 12 on the right side, which is 2 times 2 times 3. So now that I have the prime factorization, we're going to put the factors in the corresponding circles in the Venn diagram. So the first thing I look for is any common factors. Since I see that there is a 2 in both lists, I'm going to write a 2 in the intersection of this Venn diagram. So there's my 2. Then I am going to mark a 2 off both lists. I'll mark it off down here. Off both lists in my Venn diagram. Sorry, in my prime factorization, because I already put it in my Venn diagram. I have it right here in the intersection of factors of 12, factors of 18, and factors of 12. So now I'm going to keep going. They still have a factor in common, and it's a 3. So I'm going to write a 3 in the middle, or the intersection of this Venn diagram. Not sure why it's disappearing. It's very fun. All right, then you will place any remaining factors outside here so you can, until all the factors are done. All right, so now all the factors are placed in the Venn diagram. You should be able to check and make sure your Venn diagram is correct. So this circle includes 3 and 2 and 3. So 3 times 2 is 6, 6 times 3 is 18. So this circle still has an 18. The other circle contains a 2, and a 3. So 2 times 2 is 4, times 3 is 12. So this is our prime factorization, and now it's in our Venn diagram. So you can see what's happening. So using a Venn diagram for the LCM and GCF, now you can calculate or look at those values in your Venn diagram. So the greatest common factor is going to be in the intersection of the Venn diagram. So in this case, a 3 times 2, so our greatest common factor is 6. The LCM, you're going to multiply all the factors. So you're going to multiply 3 times 3 times 2 times 2, and you're going to get 36. So 36 is the LCM. Now, a nice way to check and make sure you're doing this technique correctly is if you multiply the GCF times the LCM, you will get the same answer as if you multiplied the original two numbers, 18 and 12. So if you multiply 36, since that's the LCM, times 6, because that's the GCF, you get 216. Notice you also get 216 if you multiply 12 times 18. So you have an assignment on Canvas with LCM and GCF problems. Make sure you show all your work on a separate paper and follow the directions on that worksheet. The LCM or GCF might not be your answer, but you're going to use one of those ideas to get your answer. So if you have any questions, please let me know. And we're done. Now you've completed the recording for week 9. Make sure you get all your assignments done on Canvas and let me know if you have any questions. Have a great week.